conduction. What was the answer to the kettle problem that we did in the last class? What was the answer you got? How many minutes or seconds? 6 minutes?
Sir,
Yeah, roughly.
if we increase the insulation of bomb calorimeter, will the value of CP increase?
If we
Increase the insulation,
increase the insulation, yeah,
will the value of CP increase?
I mean, if you make the insulation perfect, you'll get the correct CP. If you don't let heat pass, and if you add more insulation, it should not alter your results. If you have a very poor insulation, and there is, I mean, it's so poor that the system has to reach to a steady state which is of the ambient, then your CP will turn out to be 0. So let's talk about conduction. So conduction is something that conduction is something that happens within material. And what kinds of materials are there around you? States of material, solid, liquid, gas. So let's solids, and let me combine the liquids, gas and fluids. Fluids you can also call as liquids and gas. So let's try to combine now. So why I make this distinction? Because this is a non-mobile system and this is a mobile system where molecules are relatively free to move. In a solid state, molecules are fixed. Yes. So what are the conduction mechanisms by which conduction occurs? We saw it in the introductory class, right? Can you recall some of those?
Phonon waves.
So there was phonons or lattice vibrations, and then there was free electrons in case of metals, primarily for metals. So metals primarily use free electron mechanism, whereas other materials like wood use a combination of phonons plus free electrons. How much they'll use depends on material to material. And in liquids, what happens? It's a mobile structure, so it has it's a loosely packed structure. Yes. So what happens when you heat a liquid or a gas? Here, molecules won't move. They just vibrate along their place, and that vibration, those vibrations will carry on. Or they lose free electrons, and those electrons will carry on. In here, what happens? Molecules can vibrate and sort of diffuse out, right? So you will have molecular vibration or diffusion, right? And also what you see is, you should not confuse it with what you see in your teapot when you're making tea, and when you heat water, you see the water rising up and mixing and sloshing, right? That's not really conduction at that point. That's something else that we'll talk about in a few minutes. But I'm talking about the instance when you start to make tea, you have hotter surface at the bottom because the pan is getting hot, and then you have colder surface at the top. At those small instances where temperature difference is not so large to trigger natural convection, then you have that brief moment where purely conduction takes place. In that, the hot molecules will jiggle a bit more near the surface and the colder ones will remain on top. And I don't see any point. In general, liquids are quite poor conductors of heat. The sole conduction mechanism is quite poor in liquids. But in both the cases, for solids and fluids, you can, for the purposes of this course, we can call these properties, or we can lump these properties in parametric conductivity. Conductivity of this will be slightly better for metals, for non-metals it will be slightly lower in general, except the case of diamond. And for fluids, you will have fairly low thermal conductivity. Now to see that, can you open your mobile phones? And I have uploaded, I think it's image number 3. Can you see the image number 3? That will have the values for metals, non-metals, liquids, gases. And can you tell me in the order they are arranged? And then on the top we have diamond, because of its perfect crystal structure. So what is the order? What should I write? So first this diamond for near perfect crystal. What comes after this? Metals. Broadly, can I call it metals? There may be some exceptions. Then what? Glass. Ceramics. Is there a category of ceramics? Silicon. Glass. After that? Water. And then? Water, skin, wood, and then in the end air, steam or water? Air, no? And rigid foam, urethane. I mean, rigid foam is used as a nice insulator also. Right. So now with that, we have some idea of what conductivity is. Let's write down the base law of conduction. So what law comes to your mind? For conduction, do we know there's already some set of experiments from which a law was derived long time ago? So in about 1800, there were some experiments done by someone where they took a slab of material and they measured what is the heat flux or heat coming out of this material, heat rate. Okay, and it was found that it is proportional to, can you guess what it must be proportional to? Proportional to surface or cross-sectional area. By cross-sectional area, I mean the area which is perpendicular to the direction of heat. What is temperature difference between the two ends? Is it inversely proportional to something? So let us call it delta x, or you can also call it L. Now, if you want to write a sensible formula from all this, what you can write? What you know is the Fourier's law is equal to AC del T by del X. We need a constant of proportionality, which will depend on material's property to conduct heat for the same delta T. Right? If you have a metal versus wood, different materials will conduct different heat for the same delta T. Yes? That would be your case. Now someone wants to point out a mistake in this law, or should we add something to it? this is like if I want to write a more point-wise description, I can write this, right? So it is the negative direction of the slope. If you were to draw a temperature profile here, and let's say it decreased, so dou T by dou x is, if your x starts from here, which usually is from, origin is from the left side. So your dt by dx is negative, and your heat flows in the positive direction. So heat always flows in the negative slope of temperature gradient. What are we assuming here? Are there any assumptions that we are making? For example, can I use Fourier's law for a wood that I just chopped from a tree? I just chopped. I'm not talking about the engineering wood where everything is like this table, where everything is mishmashed together. No. Right? So even here, for example, what I'm talking about is when you chop a wood from the tree, you see some patterns, right? And I mean, these patterns you can also see on this table. I don't know if those are painted. But this is a fake pattern because it is applied over an engineering wood. But in general, you would see some patterns. And if you were to conduct this experiment on a slab of a natural wood, would you see some changes? What changes would you see?
Heat transfer won't be uniform across the entire area.
So, what property would be non-uniform? Conductivity. So this is a law, right? So I want to bring some attention here. What does law mean to you?
Observation we derive.
The observation we derive. So these are the class. So Fourier's law, Newton's law, viscosity. What other laws are there? Ohm's law, right? Hooke's law. These are all constitutive laws derived from, or I should not say derived, I should say guessed. These are nothing but educated guesses which work for wide variety of materials from experimental data. Right? Fourier's law is not truth. Right? You go to wood, what would happen? As you say, that there are some limitations here. We are assuming that A is homogeneous. What do I mean by homogeneous?
Same across the entire.
Same property. So this would be the example for a material. Let's say I take this duster, and if I had constructed in such a way that it has low density of wood here and high density of wood here, then that would be a heterogeneous structure. The property of the conductivity here is not same as here. So I cannot write a uniform expression. The example of wood that we talked about. In case of the bark of wood, so I have also uploaded the image of wood. Can you open that in your mobile phones? So that it is a macro picture and a micro scale picture when you zoom in and you see something. Is it there? So what I was talking about were these, I think it's called against the grain and in line of the grain. So you see that the picture is a bit rotated. It's not the direct one-to-one correspondence. You see these lines. These lines are something that are in the plane of the second image. So you see the air gaps between the fibers, right? Those air gaps would be something against the grain. So if these are the grains in the left image. If you are having heat flow in this direction, you would have to go and fight the air pockets that are there in the wood, or whatever gas is trapped in the wood. And generally gases have low conductivity. And if you were to perform the same experiment along this direction, you would experience slightly higher conductivity. You see that? In the second image, if you take heat transfer in the one direction versus the other, you can clearly see that there would be some changes. That would not be captured by this expression. Yes? Here we have assumed this K is isotropic. Isotropic meaning same in all directions. In the case of wood that I have shown you here, it is homogeneous. It is same everywhere, but it is anisotropic. So can you tell me Fourier's law for anisotropy? So Q dot anisotropic. Can you tell me for modified Fourier's law for a material like wood that I've shown you there? So wood Q, so let's go here. So let's say this is against the grain and this is with the grain. Would Q dot here, let me call it Q dot Y and then Q dot X. Would it be same as Q dot X for the same delta T? No. So should this be a vector quantity? Should Q dot be a vector quantity? In general, it's a vector quantity here. We did not, what is this? We did not write it here because it's a flow of, it has a direction. It has the direction of X. In Fourier's law, it is for some simple materials like this engineering wood where everything is homogeneous, everything is isotropic. So you perform your experiments here or here, given in the same delta X, you will get the same Q dot. But it will not be the case here. So you have Q dot, you should write X, Q dot Y. What will you write here?
KX.
Minus Kx, AC, dt by dx, minus Ky, AC, by dy. Yes? Another example for this is graphite. You might remember the structure of graphite, right? It is this layered by structure. So that also has, it is well known that graphite in one direction is very, very highly electrically conductive. And on the other direction, it suffers by an order of magnitude in electrical conductivity. So whatever you're learning here in context of thermal conductivity also applies to your electrostatics or electrodynamics. So another example would be graphite. So with that, let's talk about convection. And what is the basic law of convection? We performed a demonstration last time in the class. This time we are not doing it because it will be done in the UOP lab. But just a quick view of what you will do there is that in the resources section, I've given a sort of YouTube short link for a natural convection demo. So please mute your phones because it has some background music. Just can you open the link? About convection. So what do you see in that is that you have a jar and simply you keep two beakers. This has cold water and this is hot water, and you place a room temperature water over here, and you put dye, you inject dye here and you inject dye on this surface. Because of thermal gradients, you see only one side of the dye rising up and mixing, the other side just remains where it is or just diffuses very slowly. Yes? So one side is undergoing natural convection. Which fluid is undergoing natural convection? The orange or the blue one? The red or orange one, right? And when I showed this to my last batch of your seniors, couple of students after the class asked me that this is happening because of increased mass diffusivity. Because in mass transfer, you learn that your diffusion coefficient is also a function of temperature. But this is not something that's happening at a molecular scale. What you see here, this is a very fast mechanism happening over length scale which are much more than molecules. Right? Molecules are of angstrom level, and what you see here is of few centimeters. So this is a bulk scale motion. Huh? So let's talk about convection now. Now what convection is, it is conduction plus loss of fluid motion. Why do I call it conduction plus something? So convection, for me, it's always been, and some of the classical textbooks, they mention that ultimately fluid is, so let's say you have, for example, what you saw there, the bottom layer is hot, the top layer is cold, and the convection will take place. In this case, it's natural. If you were to dip your finger and move it, it will be forced convection. Yes? So, but in general, convection meaning fluid motion. But ultimately, fluid is exchanging heat. Why conduction only? What you are doing by convection is just bringing the cold and hot molecules together, so that they can exchange heat more efficiently. Does it make sense? If you were to take, in case of water in that example, if you were to take honey, right, which has a different conductivity, for the same motion that you generate, you will get a different heat transfer coefficient or different convection rates. So convection ultimately is conduction between a hot fluid molecule and the cold fluid molecule. They'll sort of share their vibrational energies. But with convection, what you do is that you vigorously bring colder chunks closer to hotter chunks. If you did not have this, the second part, then how would, or the early stages of tea making, how would the fluid reach the other side, the colder side, the hotter fluid reach the colder side? Is by vibrating one layer, and then the next layer is will exchange this thermal energy, and the next layer and so on. But by increasing heat externally or naturally, you are bringing the coldest side to the hottest side, very close to the hottest side, so that now they can do the delta T, which is locally in there, that can increase. Does it make sense what I'm doing? So let me draw, if it's not clear, let me draw the two situations. There is no mixing of fluid. By that I mean either NC, natural convection, or forced convection, and mixing, and let me call it no mixing, or stagnant layers. So let me make this hot fluid layer, and then there is cold fluid layer, and even colder fluid layer is here. So if, again, this should be inverted, but whatever, the gravity is in this direction. Okay, now if you were to make this side hot, if this is your teapot, if you were to make this side hot, the heat will slowly pass in this direction, and you are not mixing anything. So it will naturally take more time for the entire fluid to get heated up. But in this case, so this is the coldest side, moderate fluid element, and hottest fluid element. Now what will happen, because of mixing, you will not have this, but instead what you will have is, you see what I'm saying? So when the chunks are close together, you have higher conduction. Does it make sense? With that, in case of forced convection, you do it artificially. In case of natural convection, the fluid naturally mixes due to density differences. A fluid's density increases or decreases with temperature? It decreases, it expands, right? And so naturally you will have a condition where there is lighter fluid on top of, lighter fluid on bottom of the heavier fluid. It will naturally want to come up, and that will induce your mixing. Now that makes us think that fluid properties must play a major role in determining the heat transfer coefficient, right? So all this is lumped inside heat transfer coefficients. If you forget about post convection, natural convection for now, if you have a hot surface at Ts, if you have ambient surface as T infinity, and let's say there is this, you switch on a fan or natural convection going on or a mixture going on, the property that defines this convection as we saw it in the first class is the heat transfer coefficient. Yes? Now, you can naturally imagine, since fluid motion is involved, H should be proportional to, heat transfer coefficient should be proportional to viscosity of the fluid, velocity of the free stream velocity, how much motion we are generating, and density also sometimes, and all the fluid properties. So it becomes much more complex than the conductivity aspect. And again, when I draw this picture of Ts, T infinity, H, what is the law that governs convection? So if I were to say that Ts is greater than T infinity, what will define my Q dot in this case? Q dot would be heat loss to the environment, right? So what would I write? H. It will also depend how much surface area I am getting. But this is not the same as cross-sectional area, this is the surface area. HA delta T meaning Ts minus T infinity. If I had Ts less than T infinity, what would be the direction of my heat flux or heat rate? Downward? Right. So these are your two laws. And can you tell me what is the unit of H? What's the unit of Q dot? Watts? A meter square? Watts per meter square Kelvin or watt per meter square Celsius? We forgot to cover the unit for K, so let me write it here. What was the unit of K? Q dot was minus KA by dou x. There is one length scale extra here. So this would be watt per meter Kelvin or watt per meter Celsius. Okay. So this is watt, this is meter square, this is Kelvin per meter. So this cancels out. Okay, so with convection covered, let's solve a problem on conduction. And this is actually one of the experiments in UOP lab. I'm not sure if you will cover it this time, but this is something that you would do in the past. There is an apparatus, and you can also go and check it out. I think it's functioning. This is called thermal conductivity of wooden slab. So basically, we would find out thermal conductivity of a wooden slab. You would have these two slab materials, in between which we would have a heating element. So a resistance wire would go and heat it up. 50 volts of potential difference would be applied. The sides, the top and bottom sides will be provided with running water. Why running water? So that this surface to be maintained at a constant temperature. And that temperature we would know what it is. So that you can have a steady condition over some time, over an hour or so. And we would add thermocouples, basically which are thermosensors or thermometers if you would, but you could squish them inside the material so that you can take a temperature reading. And then we would see what is the delta T. Because again, what is the direction of heat? If heat is being generated here, and this is wood, these two are wooden slabs, sides we have done some insulation so that heat does not escape, and everything is one dimensional, like it happens in y direction. So if you want to conduct a simple analysis of this problem, which is basically to find the thermal conductivity of the wood, how would you do that? And if you need more information, let me know. So we need K wood. This delta T your friend measured to be 15 degrees Celsius.
The resistor value or the current passing?
The current passing through. I think the current is known to be 0.04. So voltage is 50 volts. Current is 0.04 ampere. What else? What else do you need?
Cross-sectional area.
Cross-sectional area, yes, that's also known. I think you might have to calculate it. The diameter is known, 0.05 meter. And length of each slab, if that's something you desire, is 15 centimeters, 0.1 meter. What else do you need? A running water is here. So the conditions are symmetric in top and bottom. Thermocouples are separated by a distance, so don't take 0.1. So would you need the information how much is this? Right? Because that is your delta X or delta Y. This is 3 centimeters. 0.03 meters.
Is it 1.02?
1.02. Okay, that is one of the answers. Any other answers?
0.5.
Huh?
0.5.
0.5. Which is correct. So now what did you do and what did you do?
Sir, I halved the Q that was generated by the resistor.
Did you half the Q? Then how come we are getting different answers? What is the area that you got? The cross-sectional area would be this one?
ID square by 2.
Pi d square by 4. What did you get? Let's do the calculation. What is the AC you got?
I directly substituted.
I also actually.
So tell me here which is correct. Others, please find AC so that we know. So basically the idea is, see, you have to just use, you have to find thermal conductivity. You have a resistance wire, it will generate current into voltage, would give you the power. Sorry, not the Q dot you get. So Q dot would be just simply 50 into 0.04, that is 2, right? But then you have to divide by 2y, because your heat is getting distributed both in the top and bottom. You get 1 watt. And now, how would you find conductivity? You know Fourier's law of conduction. So minus K AC delta T by delta L. The temperature difference is 15 degrees Celsius. So that would be minus 15. Yes, conductivity cannot be negative. That would violate second law of thermodynamics. So what do you get as K? Basically 1 divided by, delta L divided by AC into delta T. Which is correct. We have to come to a conclusion. 1, right? Although the conductivity of the wood is lower than that, but roughly, I don't know what is the reason. If you want to do experiment, then you can find clues what is going wrong. But generally speaking, conductivity of wood is lesser than that. We already saw it, right? Wood was about 0.17. So roughly 5 times lower than that, but maybe some experimental error is there. In a similar fashion, can we find thermal, what is it called? H, convection coefficient or heat transfer coefficient for a wire that also has a potential difference and a current? Can I run this one? So you have to calculate H. Now H does not belong to the wire, it's the wire air system. It's this, see, heat conduction occurs within the material. So K is the material property. Heat transfer coefficient is the joint property of the material and the environment. So you have to find for a wire, and it is releasing its heat outside. This is surface temperature is 152 degrees Celsius. T infinity is 15 degrees Celsius. If you need more information, let me know. You have to find H. This is all you know right now. Diameter is 0.00. Current and voltage, right? 60 volts. So Q dot is 60 volts into 1.5 ampere. Length? Okay, let's take it 2 meters. Anything else? Density? Specific heat? Specific heat needs heat. Watts. Surface area will be 0.02 meters square. Yeah. H will be Q by area by delta T. That's it. Is it not 35?
84.8.
Roughly 35 watt per meter square Kelvin. Again, units. Units are very important for you to acknowledge. Okay.